right? So we're just going to keep going with this stuff, single degree of freedom. Today we're actually going to solve this differential equation and come up with some equations. If you are a nerd like Ethan and tried doing your homework already, you can't do it all because we haven't gotten far enough. But hopefully after today, we will have gotten far enough that you can actually do everything. I'm just joking.
I have to get it done today.
I know, I'm just joking. You're leaving, you're going to Canada, you're doing something cool. So hopefully, I think by today we should get it far enough that you can do everything. And so let's proceed. By the way, what a beautiful day it is. It's like starting to cool off in the morning. It's like this is the days like I really like being a professor. Like I know, but it's only 90 for a little period of time, and then it cools off again. Like 90 in late August and early September is not 90 in July, right? It's like it's pleasant. And like walking across campus, everybody's excited right now. They're not sad yet. Like they're not you know, everybody's just full of life. Like it's awesome. It's cool. It's cool to be on campus. I talked to my niece. She's living in Bozeman and not going to school right now. And I ran into her yesterday, and she was like just stressing about stuff. I was like, you need to just go to college. I was like, man, there's literally some. Don't tell my wife and kids, but some of the best times of my life were in college. Right? It was awesome. Like I said, don't tell my wife. She knows. I tell her that all the time. But that's why I've decided to make a career out of it. Like I did meet her in college. Yeah, I did meet her in college. So that's right. She was part of my college experience. That's right. That's right. So it's not so bad. My kids, though, like kids ruin everything. But it's like I was like, gosh, you gotta go. Like, I mean, it's just fun. Like you just go and it's just like living life, and you're poor, but you don't give a shit because everybody else around you's poor too. And then like you're learning and you're making, you know. So I don't know if you all had that experience. I really liked it. But some people get a little crazy with it, right? The first years they have this freedom and they party and they get bad GPAs and then they gotta crawl out of a hole and. But as long as they come out of that whole thing. What the hell is that? Oh, it's a fly right there now. All right. All right. So let's do some learning. Okay, let's do some learning. So this is free vibration, no forcing function, no damping. We need it's a second order differential equation, so we need two boundary conditions or initial conditions. And when you're dealing with time stuff, our initial conditions of this is going to be what's the initial displacement, right? If this thing's just sitting there. Right? I mean, there's a cart there underneath it. If this thing's sitting there, nothing's going to happen, right? Like, it's just going to stay there. Like, if you don't give it an initial, if I pull it back a little bit and let go of it, then stuff happens, right? So it needs that initial displacement. Or if it's at zero displacement, if I give it an initial velocity, then it'll oscillate back and forth too. But you need those initial conditions to start. If you don't have them, then it doesn't do anything, okay? So how I would do it, like, if you said, if I didn't have the book in front of me and somebody gave me this differential equation, I actually do, I remember how to do this when I took differential equations. You assume a form of an equation, and then you take derivatives of it, and you substitute back into the equation and go. So differential equations, this might just be just a reminder. We're not going to do it this way completely, but we'll at least set it up. What you do is you assume a form of an equation of this, e to the RT. Remember doing this, right? You said, I'm going to assume that the form of my equation is e to the RT. So then and the reason you do that, because when you take the derivative of it, the velocity just becomes r e to the RT. And then the acceleration is just r squared e to the RT. Right, we chose that form because it's kind of easy to take derivatives of stuff. So then now I take those and I plug it back into this differential equation up at the top, mu double dot plus ku, so that you get this. So you go m r squared e to the RT plus k times e to the RT is equal to 0. Right? Because it's just, so I just took these guys and substituted up into that guy up there, right? And then now, if it's equal to 0, I can divide by e to the RT. So that guy and that guy go to 0. Oh, no, sorry, they don't go to 0. We just divide by those, so those guys go away. And so then this just becomes mr squared plus k is equal to 0. And then what you do is you solve for r. R is equal to, basically you get roots. You get two roots, R1 and R2 Just so you remember doing it. Do you remember doing this? You remember? Differential equations back in the day? Barely. Yeah, so you didn't really pay attention, right? So, but that's how you do it, and you get two roots, r1 and r2, and then you take that and substitute back. U of t is equal to c1 e to the r1 t plus c2 e to the r2 t. That's how you would do it, right? And from here, you take this guy and you put it into Euler identities. You might remember hearing those before. Right? Euler identities. And what that does is these guys bring out sines and cosines. The answer. And those sines and cosines are where we get our oscillations. Oscillates. Okay. That's the robust method, because I was like, that's not how, the way the book does it isn't how I would have solved it, right? I would have done it this way and I would have gotten there, right? And this is how you would do all differential equations, right? I think the book cheats a little bit because instead of assuming a form of equation like this, more general, it assumes the form of the equation in terms of sines and cosines. It knows the answer before it goes in. So that's how the old way. Just to kind of tie that loose ends. If it sounds like you guys didn't remember how you did it anyway, so maybe I didn't have to tie that. I didn't have to tie that loose end because you've purged that information. So just if you wanted to, if you were thinking about that, then you could have done that way. Okay, so book method, right? How the book does. If you open up the book, this is what it does. It says, all right, I'm going to assume the equation takes this form.
And we can use the book.
Oh, absolutely. You know what I mean? That's the thing, is we don't have to derive this. We're going to drive it today, and we're going to get an equation, and then you use that equation in your homework. Yep. So this is giving you the foundation to where that equation came from, Ethan. Yeah. You should like that.
Yeah, I do.
Right. Because you're a nerd. Right? I'm just joking. Ethan's not a nerd. Omega t plus b sine of omega t. So that's the form they say. They assume that form.
Was that a B or a beta?
That's a b. That's just b. Just a constant. So we assume that form. So then when we take the first derivative, you do the same thing. You take the first derivative and second. We don't need the first derivative right now, so I'm going to go right to the second derivative. I'll just give you what the answer is. You get you just, that omega squared just comes out front, and then there's some negatives that pop up. So what you end up with is negative omega squared times a cosine of omega t plus, minus omega squared b sine of omega t. So if you take the second derivative of that assumed form, you get that. They both have that negative omega squared on it, so we're going to pull that negative omega squared out. Negative omega squared times a cosine of omega t plus b sine of omega t. Okay, so there's your second derivative, pulled that omega squared out. I get that. The stuff in the parentheses right now is u, right? It's u of t, a cosine of omega t plus b sine of omega t. So this right here is just what our assumed u of t is. So then what we have, so this is just u. Not omega, u. So what you get is u double dot is simply equal to negative omega squared times u. Okay, so that's that, and then this is what our assumed equation for u of t is that. Okay, so then when we get to this point right here, we take that and plug it back into our differential, just like we did above. We take these new what mu double or what u double dot is, and you put it back into the equation of motion. So then let's go back to the equation of motion, and it is mu double dot plus ku is equal to 0. And so we go m times negative omega squared u plus ku is equal to 0. All right, we pull u out of this. And so we get negative m. What did I do? Negative m omega squared. What we're now is coming up with what the natural frequency is. Omega squared minus k times u is equal to 0. Right, so I just pulled the u, I just pulled it out and put it on the right. Pulled the negative out as well. And so in order for this to happen, in order for this to be equal to 0, either u is equal to 0, which is boring, or m omega squared minus k is equal to 0. Right, so this tells us that m omega squared minus k is equal to 0. Or, what do I here? M omega squared is equal to k. We solve for omega squared. Omega squared is equal to k over m. Or omega is equal to the square root of k over m. That is a big finding. So we haven't completely solved this, but we're on our way. So just got to refresh what we did. We said we assumed that u of t was a cosine omega t plus b sine omega t. We did the second derivative of it. This omega squared popped out, so it just ends up being u double dot. The acceleration is just negative omega squared times our assumed equation right there, right? So then we said, all right, let's take this newfound information, let's put it back into our equation of motion. We substitute those things in, and then we kind of worked our way through this thing. And you know, this thing has to be equal to 0. If that's equal to 0, then this omega right here has to be equal to be related to k over m, which is related to square root of k, or so it's equal to the square root of k over m, right? So that's just what omega needs to be in order for this equation to work, okay? So this right here is called the circular natural frequency. This is a big finding. We're going to use this a lot throughout the semester. It's not the natural frequency. We'll write what the natural frequency is in a little bit, but it's just the circular natural frequency. Okay, because it's in a frequency, right? It's in radian. I think it's radians per second, but we'll get to that in a second. So that's the circular natural frequency. So this just says in order for this to happen, this frequency, this omega inside this equation has to be the square root of k, the square root of k over m. Right? And this should be accepted. And we were talking at the very beginning of the semester about everything has a natural frequency, right? If I take, I showed a little demonstration, I took a little ball and I pulled it back to a certain distance and it went back and forth with a certain frequency. We mentioned before, if I take and I increase that mass and pull it back and let go of it, then that increased mass will slow it down. It'll oscillate less, right? And then, or if I had the same size ball and I made the rod stiffer, right? If I made the column stiffer and I let go of it, it's going to rotate faster, right? So the natural frequency is, just by your intuition from before, it should be related to the stiffness and the mass. Mathematically right there, boom, pops out, it is related to the stiffness and the mass. As mass goes up, frequency goes down. If stiffness goes up, frequency goes up, right? And we just showed it mathematically. So it's not quite the natural frequency, it's the circular natural frequency. We'll get to what the natural frequency is in a second. Okay, we're to that point right there, that has to happen, okay? From there, though, how much room do I got? That room right here. Okay, so let's go back. Let's finish this off and come up with our equation. So now we come back to what our u of t is. mu of t is equal to a cosine of, oh, yeah, I should have mentioned this too. This we call omega n. We're going to put an n on it at this point. Right. The n denoting the natural frequency. Later on, we're going to have a frequency of the forcing function, which we're going to call regular omega. So here, from now on, we're going to start calling that omega n. And omega n is equal to square root of k over m. Okay, a cosine of omega nt plus b sine of omega nt. Right? Now we need to apply our boundary conditions. Like a and b, those constants a and b, where they're coming from is an application of the boundary conditions. Right? We need to apply, and our boundary conditions is that u of 0 is equal to u naught, and u dot of 0 is equal to u naught dot. Right? So let's apply those boundary conditions. So u of 0, or u of t equals 0, is equal to u naught, which would be a times cosine of omega n times 0 plus b times sine of omega n times 0. Right? So sine of 0 is 0. Right? Cosine of 0 is 1. Right? So then u naught dot, or sorry, a is equal to u naught. So that tells us what that boundary condition is, right? Or what it tells us what that constant is by applying the boundary condition that's equal to 0. The displacement is equal to u naught, rather. Okay, so then we do this one. Then we do the same thing for velocity. U dot of 0 is equal to u naught dot. U 0, this would be negative omega n u naught sine of omega n times 0 plus omega n times b times cosine omega n times 0. So I just took the derivative, just one derivative of this, right? And I plug t equals 0 into it. That's what this is. This is one derivative of t equals 0 there. And so this guy's 0. Right? This guy's 1. And so we could solve for b at this point. And b equals u naught dot over omega n. Okay. You might make note that these are the boundary conditions. Just so you know. Just so you know what we did there. Applied the initial conditions. Right? And so if you put it all together, this is it. So that is the equation that satisfies that equation of motion, right? The equation of motion, mu double dot plus ku is equal to 0. This equation solves that, right? And it has those initial conditions, what the initial velocity is and what the initial displacement is. And so that is the displacement as a function of time for that. Beautiful, right? That's what you need. You need that guy, right? So you don't have to do that derivation every time, but just knowing that like this is it right here. So you have u naught cosine of omega nt plus u naught dot, so the initial velocity over omega n times sine of omega nt. And then in this equation, omega n is equal to square root of k over m. Okay. So let's talk about. We talked about the yeah.
Which equation of motion did we just solve?
We just solved this one. Free vibration. Yep, we're right in the middle of. We're right in the middle of free vibration, no damping. Right? So then we'll end up doing this for free. So then now there's 2 bugs. Now there's also free vibration with damping is the next one we're going to. And then we're going to do forced vibration without damping. And then we'll do forced vibration with damping. That's our path forward. Yeah.
So free vibration means static?
No.
No.
Static means it doesn't move at all.
Okay.
Right? Static, that's the definition. Free vibration. Now there's 3 bugs.
Why are there so many bugs in here?
I don't know. Windows open, heat lamp, all these little guys. There they
They
are.
do
Right there.
come out more in the fall.
So this is. I don't like I didn't put a cart underneath that, or I didn't put wheels underneath it. So there's. Right. So I got this guy. What this is all we're modeling is this. I've taken this thing, I've pulled it back to a certain distance, and I let go of it, and then that thing's gonna go. Right? Or I could have had it here, pulled it back, and thrown it at the same time. It could have an initial velocity and an initial displacement.
Okay.
Right? The equation for how much does it displace this way, and then this way, then this way, then this way. That equation is this.
Gotcha. Okay.
Is this right here. Right? That's the equation that says how much that thing displaces. Okay? So what does that look like? I mean, there it is. That's what that looks like. If you plotted U of t, right? This is a plot of U of t. This one has an initial velocity and initial displacement. So we've displaced it initially, U naught, and then we've also given an initial velocity too. We throw that sucker, and then it'll go up to a certain point, and then the spring starts getting engaged, and it comes back down, and the spring gets engaged in the other direction, and then it comes back up, and the spring is going in the other direction, and then just kind of like, just oscillates like that forever. Then
So no damping just means
This-
there's no energy loss.
no energy loss. It will do this forever because there's nothing in that equation that's pulling energy out of the system. When we add that damper to it, then which is the very next step is then we get the equation, this equation out front. Only flash down to it. There's a little foreshadowing. So this is it with damping. We've got this, oscillations, and then you have this out front, which is a decay. And so this decay comes from the damper. And so that causes it to, it'll keep oscillating, but it's adding a component that's pulling energy out of the system, and it's decaying. So it's gonna do, there's a couple different things, but it's gonna do this, right? It's gonna oscillate, but then that e to the negative term is pulling energy out of the system, so it's decaying. Our current state where there is no damp, which isn't real. You don't have that, right? You have this, but you don't have what we just solved for, no damping, right? And since there's no decaying component to it, this thing will just continue to oscillate forever like this. Okay? Make sense? Real cool. So this is the plot of how much that cart displaces both directions, and it's dependent on what your initial velocity and initial displacement are. Okay. Now, let's come back up here in terms of this. Let's close the loop on this frequency. I said that was the circular natural frequency. Okay. Now, you can see right here, it completes one whole oscillation between here and here, right? So it's at a zero displacement, then it goes up to the max displacement, then the max negative displacement, and comes back in here. And so that distance right there, right, is what they call the natural frequency, or natural period rather. That's the natural period. How much time does it take to go between, or to do one whole cycle, okay? If we come back up here, right, and we look at this is sines and cosines. How often does sine and cosine do one whole circle, or one whole cycle? 2 pi, right? So it goes over 2 pi, cosine goes from 1, it goes from 1 to -1 back up to 1, cosine does. And then over one whole cycle, sine goes from, over 2 pi, sine goes from 0 and then back to 0. Okay? And so that's so over 2 pi is when we get this thing happening. So what you do is you say 2 pi, you get 1 cycle. You get 1 cycle. Right? Just how sines and cosines work. And so what you do is you call this, you say omega n times Tn is equal to 2 pi. Right, so in here, what I did is just say, well, this right here, omega n times a time, is got to be equal to 2 pi. Right, that's when I get one circle, is when this stuff on the inside. And then I'm just going to call that Tn. And we're going to solve for how much time it takes to do one cycle. And so there it is. I mean, Tn is equal to, oh yeah, right there. Oh, look at me. Let me plan it ahead. Right? So Tn is just 2 pi over omega n. So if you calculate what omega n is, which is square root of k over m, that'll give you a value. You do 2 pi over that value, it'll tell you what your natural period is, how much time it takes to go over. And then you do the inverse of the natural period, and it gives you the natural frequency. And so that's simply is 1 over Tn gives you the frequency. So time is seconds per cycle, frequency is cycles per second. So you just do the inverse of the natural period, and then that's the equation right there. So we're going to use these terms pretty interchangeably. I don't think we call the circular natural frequency out too much. Usually you call out the natural period, and then or you call out the natural frequency, one of those two. But we kind of use them interchangeably throughout. So that's where those things come from. Everybody cool? Cool. Right? So here's just a graph of what's happening. Like we just covered this. So this is just, you can see what one whole cycle is happening. It's 2 pi over omega n. Initial velocity at the beginning will give it a ramp up, right? So this is, I pulled the cart back and I threw it, so it has an initial velocity, so it's going to displace a little bit more. Right? Or actually, what this is I had a cart and I threw it in the same direction as I had my initial volt displacement. Pull the cart back, and I pulled it really quick, and then it displaces a little bit more, and then it starts oscillating back and forth. Right? And then this is just kind of showing you, like, at point A, it has 0 displacement. It's doing it in terms of frames instead of carts, but A, there's 0 displacement. B, it's displaced most to the right. C is back to 0. D is displaced most to the left, and then E is back to 0. So it's just kind of showing you this thing is oscillating back and forth. Should we get a fly strip in here? Those are grosser. Fly strips are gross. Is it grosser? Or have the...
Do one of those guns that shoots the salt.
Salt?
Yeah, you ever seen it?
No!
It nails the flies with like a big...
It's like a shotgun.
Yeah, the salt. It's fantastic.
Let me get one. Do you just buy these things?
Oh, yeah.
Do they really?
Yeah.
A fly shooter? Just a shotgun blast of salt?
Yeah, it's called bug assault.
Bug assault. I want one. Maybe I'll get one. Just shooting bugs out of the air in front of you. Skeet shooting. All right. You know what? Yeah. Hell, one of my favorite places to eat in town was Taco Montes because it's really close to here. Taco Montes has a major fly problem the last couple of years. And I was like, God, you guys just need to hire somebody to come in and take care of these. Or get bug assault. Right? I'll get one and I'll leave it on there. Okay, so the book then goes on. We're just following steps through the book, right? So the other thing is they do this amplitude. They talk about amplitude. When would you find this max? Like if we were back to calculus, if I said, hey, find the max, what's the max displacement? What happened? How do I find that? Yeah, velocity is equal to 0, right? When velocity is equal to 0 is where it's like kind of, it's just right on the cusp of going back down. And so then that velocity equal to 0. And so the book goes through and does all these steps. But basically they just say, yep, u dot of t. They set that equal to 0. Then what you get out of that is what t max is. Right? When you set that equal to a t max pops out of it. And then you come back and you say, well, u of t max. Right? That gives you u max. Right? And that's what the book has done. And that's what they call the amplitude there. I think that might be, you could be a little careful with it. Yeah. I mean, I think the true definition of amplitude is, I think it's this. Like the overall range. But the way they've defined it, I don't know, I'd have to look back. But I think the way they've defined it is just how much displacement from the 0 displacement have they gone. Okay. So that kind of closes the book on that thing. Okay. The other thing to note is there's another way to write these equations of motion. All right, and it's kind of a compact notation, and you'll see this happens a lot. The beyond us, this shows up in sound and all sorts of stuff, but if we want to write the same stuff, the same method here, what we do is we're going to define just kind of a shorthand notation. We're right from the get-go, we're going to say that omega, or we're going to say that omega n is equal to the square root of k over m. And then so omega n squared is equal to k over m. And so I just square that, knock that thing off there. And if I come back to my differential equation, mu double dot plus ku is equal to 0. I'm going to divide everything by m. So I'm going to get this. U double dot plus k over m is equal to 0. Oh, and I lost a u. Let me finish. I wasn't done yet. Just a test. Okay. And then k over m is just omega n squared. So this is just this. I think your notes might be a little bit different. I think I had an extra m out front. Is that right? Yeah, so to cross that m out. There's no m there. I've fixed it for future generations, but not you guys. Right. So that's our differential equation in shorthand notation. Computers like it this way better, right? Or a calculator would like it better this way. Like this assumes the k over m from the beginning, and this is just, it makes for a cleaner solution method. And then the book does this a lot. Like we're gonna get into this a little bit. You kind of divide by m, you substitute in that omega n squared for k over m, and then this is the first time we see it. We're gonna do it throughout the rest of the semester. So that's just kind of introduce you to that. That's all it is. It's the same equation. It's just you just do this substitution, right? Omega n squared. Divide by m, get that out of it, and leave it like this. Okay, that's it. I want to say. All right. So then, one way there's the book method for solving it. There's the way that we did, the robust solution. Or really, truly, if you had asked me just from get-go, said, hey, will you solve this differential equation? I would immediately go to Mathematica. I would go to Mathematica or MATLAB, one of the two, and I would have Mathematica or MATLAB do it for me, because why the hell do I need to do it when the computer knows how to do it? So this is just to show you, I don't think we're going to use Mathematica in here, but if you wanted to, this is just what I plugged in there. I just said, in Mathematica, this is differential solve, second derivative, right? This is u double dot plus omega squared times u of t is equal to 0. And then I plug in the initial conditions. U of 0 is equal to u naught. The velocity is equal to u p naught. And I want to solve for u of t, and then the variable is t. And I say simplify it, and then it pops out like that. Just like that. There was no assumed form of the equation. There was no, it just robustly let the computer do it. That's the equation that we just spent the whole time deriving, just with one little deal, right? See, this is why I use computers to do this shit, right? Because you purge, you have differential equations, you can just purge it all and don't listen to it again. Don't need it again. Okay, so then I just went on and just kind of substituted in with the K and the MR and stuff like that, just to kind of show, and then I just plotted it. This is the plot of the displacements, and this is the plot of the velocities, right? The velocities are just the derivative of the displacements. And so this one had an initial velocity because it starts out at 10, so that means I have an initial slope right there. And just to kind of show you how you go about plotting them and stuff. MATLAB, you could do it in MATLAB. You do it whatever you want. This is future stuff. We're going to come into this later. This is solving. What we're going into is how to solve when there's a damper. That's the solution for the damper. Those are the three different. We're going to see there's kind of three different cases when you deal with dampers. Okay, but we'll come back to this one. These are just kind of premature. Those are premature. Okay, gravity. What do we do with gravity? This is the static stuff, Ethan. This is stuff you're asking about. Okay, and this is confusing, but I think I got a good way of explaining what to do with it, right? Because we always do our cart on the side, right? And I told you before, we're doing the cart on the side, so we didn't have to deal with gravity because gravity's there. Okay, so but if you do turn it this way. All right, I think one of your homework problems has a thing where it's a beam, but not this, but it's a beam, but it has it like vibrating vertically, and then it says something about this static displacement. You're like, what the hell do I mean by static displacement? So hopefully we'll cover that here. There's a way we can simplify this down and make it easier. Okay. So, we got this thing. All right. So, all right, done a lot of the stuff here. So in this particular situation, right, we look at this, we take that system and we draw our free body diagram. We're going to say downward is positive u. And then in this case, now we got mg going down, and then we got ku going up. Okay, so we picked up like a forcing function, right? A constant forcing function that's just applying a load down. So if we were to draw, we sum our forces and set it equal to mass times acceleration. So if we were to do that, you say, yep, we go negative ku plus mg is equal to mu double dot, right? So sum of the forces is equal to mass times acceleration. So I got mg going down, that's positive. I got ku going up, that's negative, right? I put all the u terms together. And so I got mu double dot plus ku is equal to mg. Right, so there's our differential equation. That's our equation of motion, our differential equation for doing this. The problem with that differential equation is that this is now non-homogeneous. Non-homogeneous. Thank you, Apple. I think it's actually we could do as one word. Right? If you have a non-homogeneous differential equation, then this is where things are a little more difficult. Like I mentioned before, you have to get particular solution and homogeneous solution. You have to do both of those, which is something I don't want to do right now, and I don't think you want to do it either. But it gets it. Later on, we're gonna have to do it, but right now. But the point here is that it's difficult, right? And then hard to solve via traditional means. You can do it. I mean, the computer could do it really easy, but we're going to use a shortcut. Right? We're going to treat this thing slightly different. This is what the book does too. But if you plug this thing into the calculator, it'll pop out. Sorry, not the calculator, but the computer would have no trouble solving a non-homogeneous differential equation, right? But the difficulty arises with the particular and homogeneous and stuff like that. So what we're going to do is we're going to introduce this term called the static displacement. Shortcut. Introduce introduce a static displacement. What the static displacement is, if I just had this system right here, if I had that system and it was sitting there and I just kind of slowly, like if I let go of it, it's gonna oscillate. But if I were just to kind of gently lower it down until it was like in a good place, I could probably use the same cart that someone's going to make me for demonstrating, right? Yielding. When you make me that cart for demonstrating yielding, I could probably use it for this too. I could hang it from, anyway. But if I kind of gently laid it down, this thing would displace a certain amount, right? It would kind of come down a little bit and then kind of just hang there at a static displacement, right? It would displace that thing. We can calculate that displacement really easily. And that's what we're going to call delta static. Delta static, right? How would I calculate that? What would that be? What's that? Close. Wait, we got mg coming down. Yeah, the spring point. But these guys would be equal to each other, and then if I wanted to solve for what that displacement is, I would just do mg over k. It would tell me what that displacement is. Right? You're exactly right. You'd say ku is equal to mg. That's when the things would be in equilibrium, right? And then if I wanted to see how much it had to displace for it to be equal to mg, I would solve for u. U is equal to mg over k. So delta static is just mg over k. Everybody see that? Why that would be? I mean, we could do. I mean, you could say, I've never actually done that, but that's a great way to think of it, right? Mg would be equal to Ku, right? And then U is equal to Mg over K. I like that. That's a great way to think of it, right? And that's what we're calling delta static. Okay, so what we do, so the first thing, kind of step one, calculate delta, come on, bro, delta static. Step two, solve homogeneous equation. Right, which is, u of t is equal to u naught cosine of omega n t dot, right? That's what I mean by solve the homogeneous one. And three, u totes is equal to u of t plus delta static. Give me my delta, give me my delta. Okay, and so what the shortcut is it basically says, and the book goes through and it proves this is fine stuff, or at least discusses a little bit. But the idea behind it is the thing is gonna oscillate the same as if it was on its side, like it's gonna oscillate back and forth. But instead of oscillating about 0, it's going to oscillate about that static displacement. So it kind of like it lets it down, and then it oscillates down below. That thing just causes it, that mg just causes it to sag a little bit, and it oscillates around the sag.
So you're setting, in step 2, you're setting that equation to delta static, right?
You just solve for delta static, just being mg over k, and then you set that aside. Then you come back and you calculate u of t, just u naught cosine of omega n t, the square root of k over m, just like the stuff we did before. And that'll give you the oscillations. And then the total displacement will be the static displacement plus what you just found with the oscillations. Okay? And so just graphically what that looks like, right, is this, right? So this thing's going to oscillate back and forth, right? This thing's going to oscillate back and forth. It's raised up a little bit, and we let go of it. Downwards negative, or downwards positive, right? And so instead of oscillating around the 0, so this would be 0. This one here is 0. Instead of oscillating around 0, it oscillates around mg over k. And that's a lot easier than doing it the other way. So this is when they said in that problem statement, what are the displacements about the static displacement, right? Isn't that what the problem statement says? Something like, what is u? Yep. Yep. From the static displacement. So what it's after is just it's just after this. Yeah, it's after what you use with your equation. It doesn't want, like, don't add the static displacement on top of it, right? And so because that one it's this way, right? It's a beam like this. Right, the beam.
I think this one is the one.
Oh, it's a
that's
bar.
hanging down.
It's what?
It's the one that's hanging down off of the rod.
Oh yeah, okay, yeah. So it's just after. Basically, what it's after is just ignore the mg term, is what it's saying. Ignore the fact that there is a gravity term there. But if you were to do it, like when we're dealing with, like, say if you were designing, the next homework does have it. It has a beam and has a load on it, and then it's going to oscillate. If you're designing that beam and then it's going to oscillate, do you care about the static displacement? Absolutely, right? Because that's making the beam displace more, right? So it's going to oscillate, but oh, by the way, it also has gravity there too, which is going to make everything displace a little bit more. It's going to increase your loads on your beam. Okay? But it's basically it's a kind of a clever way to kind of like, oh, if it's vertical and you got to deal with it vertical, just pull the delta static out, solve it as if gravity wasn't there, and then the total displacement will have the oscillations plus that static displacement. And in that particular problem, it says just ignore the static displacement and what's it going to do after that. Cool. I think you're far enough to make it through the. I think you're far enough to make it through that homework.
That's only like halfway. Yeah. That's 1.5.
Oh no! But what's the rest of it though? What's the rest of it?
That's the one where it's being
Let's look at it. Very good. Let's look at it. You got 5 minutes. I didn't know what I was talking. Didn't know what I was going to talk about anyway. So this is perfect. All right, that one's fine. That's just driving the equation of motion. This one is driving the equation of motion, right? This one's driving the equation of motion for this guy as well, right? Which one are you doing to this one? This bottom one, right? And so the key there is what do you use for the stiffness, right? Because this one is a fixed, and so what in the center here, this is your spring, is this thing bending, and so you just got to figure out, how does that displacement relate to the material properties and stuff like that, and end conditions, the end conditions. So I'd look up a steel manual. And fixed, and K.
We're just solving for K, basically.
You're solving for K. You're finding K.
Okay.
Yeah, you're finding K.
Will that equation equal 0, or will it equal W?
It'll equal the weight. This is back to the gravity thing,
Yeah.
right? So for the differential equation, there is no W there. Right? For the differential equation, there is no weight of an object there. That weight will cause it to sag a little bit, and that's what the mg term is. But if you're looking at the oscillations, this thing would make it sag a little bit, and then it would oscillate about that. So you don't. So what you do is you say, you're just trying to find what numbers have to be multiplied by p to give you u. And then p is just a value that's going to go into the thing. So you just pull out the stuff that gets multiplied by u, and that's what k is.
Okay.
Was it PL cubed over 40ADI? Is that what the?
What? Yeah, U equals PL cubed over 40ADI.
Yeah, and so it's that inversed. But anyways, that's just you play with it a little bit. That's just finding the stiffness stuff. We've covered all that stuff. Same thing with this one. This is the one that says something about the static displacement. So just ignore the fact that it's vertical, basically, in this one. And then think about the stiffness of this and how, this moving down, how it's related to displacement as well. Okay. Right, same deal here. This one's just messing around. If 13 is one of it, it's just messing around with the end conditions of those columns. And what you use for that, I'd look in the steel manual for that one as well. You can find that case in the steel manual to figure out what the stiffness of those columns are. 2.1 heavy table is supported by flat steel legs. Natural period in the lateral vibration is 0.5. This is messing around with frequencies and stuff, which we just covered, right? Because this is, what is it? This is a frequency. Or it tells you a natural period here, but with an added mass. So this is just playing around with what Tn is, right? So Tn is going to change by adding that mass, and then you kind of set it up and have I envision it being like a couple of equations with a couple of unknowns, and you solve for what the stiffness is, like the unknown, I believe, and so the stiffness and the mass or whatever. So that's that one. This one is the weight of the wooden block is shown. His spring stiffness is 100. A bullet is weighing 0.5 is fired at speed embedded in the block to determine the resulting motion of the block. And so this one is just. This is the resulting motion of the block, U of t. We just came up with the equation for that, right? When this thing, and what is this bullet going to do? It's going to add an initial velocity to it. And so you just have to find that initial, what do you got to use to find that initial velocity?
Conservation.
Yes, you cannot use conservation of energy, right? Because energy is lost with that impact, right? I spent first time I taught this, it was before I taught dynamics, and I thought you could do it with energy, and so I spent a day trying to figure out why I couldn't get energy to work, because there's energy there, and when it slams into the thing, then clearly energy is going to be conserved. It's not conserved. Energy is lost when that bullet hits that thing, and the wood is deformed, and what's still magnificent about conservation of momentum that it account no matter what happens inside of that thing, no matter what, how the energy is dissipated from the friction and the bullet deforming and the friction associated with that, no matter what, momentum has to be conserved, and that's how you get the initial velocity. So that just gives you U naught dot as you go into that one. And then this one, I think you could do this one almost with all of energy, but then the same idea. This thing is, once it's down, it's just going to oscillate up and down with that equation that we just derived, but what we're getting is the initial displacement and the initial velocity for that one. So everything's there. It's just how you come up with it. I think you could do this one with energy right from the get-go. Like the maximum displacement of the object out at the bottom. I think, anyways, but you could double check your answer that energy would work. You all potential energy at the top to all potential energy down at the bottom, but that's with that. I know that the static displacement is in there somewhere, and so kind of like if you can't quite get it, then that you might not be accounting for the static displacement in there completely, because there is going to be an mg component acting on that thing, so you have to play with that a little bit. But other than that, you got everything. We did it just today. Just almost like I planned that out. I didn't plan it out, but it's almost like I did. What's that?
Not have it on the
Yeah. For you nerds that tried to do it early.